Welcome back, everyone, and let us now reveal the question of how can we actually overcome this problem of clustering in such a way that we capture the local correlations. And as I've highlighted here, in contrast to a previous slide, it's all in the keyword local so far. So PCA itself is a clustering approach, is a dimensionality reduction technique which performs or applies the dimensionality reduction globally on the entire data set. So what we kind of need is a type of PCA which performs this dimensionality reduction on a subset of the data, in some way intelligently on a subset of the data. And so as it is in this word of local, there exists indeed a method known as local PCA. And first we thought that one of these first correlation clustering algorithms would be Oculus from the year 2000. However, it turned out, nope, there's also one from 1997 by Kamtala and Lean. And there it turned out, oh, wait a second, it is actually even older than expected, because it has been first proposed as fast nonlinear dimensionality reduction at the so-called NeurIPS conference in 1993. So that's quite some dinosaur, one would say, in this area. However, it's interesting how or with which intent they first wanted to use this local PCA, because they thought, well, how can we capture nonlinear properties of a data set? So suppose we've got a parabola like this, a PCA would not quite capture this parabola because it's a linear dimensionality reduction technique, unless you're using kernels, I know, but let's consider we're not using any of these kernels. How can we actually capture this parabola? And the idea that they had in mind, the authors here, Kambatla and Klein, was that you have this parabola and you approximate it piecewise linearly. So like you approximate this part of the parabola, then this part of the parabola, and the part which is close to the vertex of it. So the core idea behind local PCA is to, as it is in the name already, to discover local regions within the data and compute there in these local regions their arbitrarily oriented subspaces simultaneously. So in contrast to PCA, which computes, as mentioned before, one global arbitrary oriented subspace, local PCA gives you, as a result, multiple local arbitrary oriented subspaces. And the way it actually achieves this goal is by performing a vector quantization, which boils down in this particular case of this work to applying k-means. So the k-means, as you know it from probably previous lectures. However, the interesting part is that this partitioning of the data is performed depending on the projection. So depending on how or where it is projected, based on that information, also partitioning is made. So we've got something like an interleave between finding adequate projection and at the same time finding adequate partition. And let's take a closer look how this algorithm works. We go through each of the steps. So this local PCA, in the very first part, it initializes k centroids by randomly choosing samples from the data set. So in contrast to k-means, where some random vectors, so-called initial seeds, are computed, which are non-existent or can be non-existent, in this local PCA, it says, now we are not taking the non-existent random seeds, but we take them by randomly sampling any of the existing objects in the data set. And with this k initially chosen samples from the data set, we initialize the corresponding k local variance matrices set to the identity matrix. So for each of these centroids Ri that we have chosen, we compute the corresponding local covariance matrix, sigma I, and initially, because we have no information so far that we can rely on, we say, you know what, set it to the identity matrix, set it to some kind of like a neutral element, in this matrix multiplication. What happens next after having initialized randomly the centroids by sampling them from the data set and by initializing covariance matrices? We start partitioning the data set into K regions, denoted with R1 to Rk, and where it holds that if you're given X with centroid Ri, that this distance is smaller or at maximum equal to X and distance to a different centroid Rj. So this is what it holds. Translated, it means make sure that you cluster in such a way that it holds for every object X, it is as closest to its own centroid Ri, but in worst case, equally distant to another centroid Rj, but not closer. I mean, which is kind of trivial because you say, if I've got a cluster, an object to assign to a cluster, and you wish to have this object be as close as possible to that particular centroid. And this reconstruction distance dxri, it's called reconstruction distance, we shall see in a moment why it has this term, is further defined as d of x rj or ri, excuse me, is x minus rj transposed times some ominous matrix capital pi j times x minus rj. Wow, quite a lot of letters. So let's disassemble this piece by piece. What does this x minus rj transpose or non-transpose actually mean? This means here we're computing the distance of an object x to its centroid. Or it's actually, you can think also other way around. We're like centralizing the object by dragging it to the center of this. So this is the meaning of this left and of the right part. The matrix here that we see, this matrix pi of j, this is the so-called projection, which is orthogonal to the local m-dimensional PCA subspace. Now, what the heck is the meaning of this? So in this matrix, we have like the information, we have like the information, or so to speak, the trailing eigenvectors later on, we shall see, on which we are projecting the data to the m-dimensional subspace, where m denotes the eigenvectors with the largest m largest eigenvalues, so with the m largest variance that it exhibits. Because this matrix pi j, again, to decompose it, is a product of a matrix pj transpose times pj, but we're still not getting any more clever. What is the meaning of pj? Pj here denotes an m times n matrix, where the rows of this matrix pj, they represent the trailing eigenvectors from the covariance matrix sigma j that we have here. So what we have here is like a product of the trailing eigenvectors of this covariance matrix that we have here transposed times themselves. And this is the reason why this matrix pi j is the projection orthogonal to the local n-dimensional subspaces. Excuse me. But still, I mean, when we are dealing with these terminologies, you may say, I haven't understood a single thing about that. So let's kind of dive a bit deeper into this by interrogating what is actually the semantic, what is the meaning behind the reconstruction distance. So the reconstruction distance itself is the square projection of the difference vector, an object x, minus its corresponding mean, or metoid, so to speak, on the trailing eigenvectors of the covariance matrix of a region. Still not any more clever, but maybe this may help. So this expression above is equivalent to stating that it expresses the squared Euclidean distance to the linear manifold also known as the subspace, which is defined by the local m-dimensional subspace, spanned by the m eigenvectors of the local PCA. So in other terms, consider this pen here is like the m equals 1 highest corresponding eigenvector with the highest corresponding eigenvalue. Then this distance is not measuring actually the distance of the object to the centroid Rj, but it is computing the distance of the object orthogonal to that subspace, to that one principal component, one-dimensional principal component, where the distance to the actual centroid is minimized. So what this function actually does, it is not seeking for the distance which minimizes to its prototype Rj, which would be here in the middle, but which minimizes the distance orthogonal to that particular subspace. So this means that clustering with this reconstruction distance minimizes the reconstruction error, or in other terms, the deviation of objects which are orthogonal to their respective arbitrary-oriented subspace. So clustering with this distance function has the sole purpose that you want to find this arbitrary-oriented subspace in such a way that it minimizes for all the objects belonging to that particular cluster, and therefore the subspace, that their distance to this cluster orthogonally is kept to a minimum. And still you may say, it got a bit better from the understanding, but still not clear. And this is where illustrations come really handy. So this is a figure which has been taken from the actual paper. And what we see here on the left side, we see those two regions, R1 and R2, which can be the potential clusters. We have here the small letter R1 and here R2. So these are the corresponding centroids or medoids actually of the respective cluster. Then we have here like the m equals 1 principal component that we have here. It's called E1, and here the one principal component of region 2, which is E12 that we have here. And here on the left-hand side, what happens if we just calculate the Euclidean distance? Well, calculating the Euclidean distance of x would mean let's compute the distance of x to R1 and of x to R2. Okay? And based on that figure here, on this left-hand side figure, we would say x is actually closer to R1 and therefore belongs to cluster capital R1. But what happens if we use this so-called reconstruction distance? Then I wish to guide your attention to this right-hand figure. Here we recognize that we are not computing the distance of x to any of these centroids, of any of these prototypes, but orthogonal to the actual computed first principal component in this case. And also here, we compute the distance orthogonal to this first principal component of region 2, while here this is the distance orthogonal of that object x to E11 to that subspace of region 1. And what we discover here, in contrary to the left-hand side, is that x is way closer or is more in the vicinity of region 2 than it is to the cluster of region 1. So for the Euclidean distance left, the distance of x to its closest reference vector R1 and R2 is computed, yielding R1 here as the closest region. But if we select or compute the reconstruction distance, as you have seen the slides before, then the distance of x to its closest subspace or leading eigenvector is here that one belonging to region R2 and not to R1. So one insight is that the reconstruction distance does not account for the distance along the leading eigendirection. So it doesn't care if it's here or here or here, but it accounts for the distance which is orthogonal to them. So this is the main idea. This reconstruction distance has the property that it kind of rewards closeness orthogonal to that subspace, to that leading eigenvector, but it punishes, but does not reward it if it's any different among this one leading eigenvector. Excuse me. Now that we have hopefully a bit better understanding of the reconstruction distance, we now move to the third step. So first step was like initializing also covariance matrices. The second step was to compute the reconstruction distance. And the third step is to compute the generalized centroid. How is this generalized centroid computed? Well, for every object of a specific region. So let's say we have like here, this is region 1, this is its corresponding subspace, this one leading eigenvector. We keep it simple, one-dimensional as example. And we have several objects. And for every object, we compute this reconstruction distance of x to its centroid. And then we average it. So this is what we have here. And from all these averaging of these distances, we take that one with the lowest distance. And that one particular object with the lowest distance is then considered as the new centroid. At the same time, we're going to update the covariance matrices by how is the covariance computed. If you recall it from the lessons of Professor Kröger, you have an object X centered, which happens by this minus Ri, because this is like the centroid, and multiplied with itself centered transposed. Then you obtain the updated covariance matrix. And from that covariance matrix, you can perform an eigendecomposition, meaning that you can get from covariance matrix to an eigendecomposition the eigenvectors and their corresponding eigenvalues, where again, the eigenvectors represent the direction of the largest, second largest, third largest, and so on largest variance. And the eigenvalues, they express like the magnitude, how much is the variance, so to speak. And actually the steps 2 and 3, they are repeated and repeated and repeated, like in k-means, until convergence is observed, meaning that you have only a fractional change in the whole stuff that you can see, or that the average reconstruction error is below a specific threshold. So you can also say, okay, you know what? I've chosen the subspaces in such a way that the deviation of the objects to that subspace are so marginal that it's good enough. This can be also a stop criterion. So far about local PCA. Let's sum it up, wrap it up, the whole stuff. So it is probably put into brackets only because we have discovered that in 1993 was this algorithm. It doesn't mean that there was not any before. So also a challenge for you, if you wish to check out Google Scholar or any other source and see if that is really the oldest one or not, challenge me, write me on via email or ask for a Zoom meeting or something that we discuss about it if you should find any older algorithm. I recall that there were also algorithms regarding PCA that were much, much older than expected. So you never know. So I'm excited if any one of you is seeking if there's an older algorithm than this one from 1993. Then the second insight is that local PCA assigns each cluster its individual subspace. So we no longer have this one global subspace trying to find clusters in there, but we have for each detected cluster its own individual subspace computed from a PCA on that particular cluster, on that local subset. It combines, and this is the take-home message also, combines the k-means, so vector quantization approach, with a specific distance function, which respects the deviation of objects to the subspace. It comes with 2 parameters. With one parameter, you can control the number of clusters, like in k-means. And with the second parameter, you can control the dimensionality of the subspace. So consider you've got a 3-dimensional data set, and you say m equals 1. then it will start to find lines in your data set to which the objects can be projected. It will partition it in such a way that it yields you k one-dimensional subspace clusters. If you say, no, I want to have m equals 2, then it will try to find you planar, so planar correlated subspace clusters in your data set. It relies on a reconstruction error or distance function, but no algorithm is perfect, especially not if it's the very first one. That's it has to be considered. One contra is it has no outlier handling. However, in k-means, outliers may affect the way that the partition is formed. So it may influence your clustering. Here you have even a second impact, a second potential target. It may not only affect your clustering, but it may also affect at the same time the subspace orientation in space. So how is this one oriented, and the translation in space. And this is a terminology that I've been conducting some research on it during my PhD, that can be subsumed on the term of subspace poisoning. If you are interested and say, oh, this is quite interesting, it is a bit of a destructive way, because I was like, how can I actually destroy or massively manipulate, skew the rotation, orientation, and translation by introducing a minimum of change? So how can I achieve that? And if this is something where you think, yeah, I want also to see how I can hack this particular algorithm, then do not hesitate to contact me, and together we will be a bit of like destructive and try to see how we can hack, which in the end is constructive, because we're doing it for science and for fun, to see how actually what are the strengths and weaknesses of this algorithm, further regarding the robustness or resilience. And yeah, you may be kind of interested, because as I've had in a discussion with a colleague, there are in neural networks cases where you have this one pixel manipulation. Excuse me, I need to drink after that video. And it was impressive that by changing in certain cases 1 or 2 or maximum 5 pixels can make the neural network to detect, instead of a car, detect a dog or a cat. So it has been hacked with a minimum of manipulation introduced. The same I'm excited to find out here. How can we manipulate or cause a maximum of deviation or manipulation by introducing a minimum of change to that algorithm through the data, by like introducing data objects which are more outliers or less outliers, or micro outliers or mutual outliers, and so on and so forth. So if you've got interest into that, I'd enjoy to work together with you on that matter. Bachelor thesis, master thesis, whatever you got there in mind. Well, this was it for this video. I will get a cup of water, and thanks for joining in here. See you in the next video. Take care, and bye-bye.